All right, let's get right into it. When we think about making predictions with data, our minds often go straight to drawing a nice, clean line through a bunch of points. But what happens when the real world just isn't that neat? What do you do when the patterns are curvy and complex? How do we predict things like house prices when the relationship isn't a simple, straight line? Just look at this, a basic linear model which has completely failed to understand what's going on here. It's trying to force a straight line onto a pattern that clearly has its own twists and turns. And this is a massive problem in machine learning, right? Because if your model can't even see the basic shape of the relationship, its predictions are going to be way, way off. And that really brings us to the big question. How do we build a model that's flexible enough to actually follow these kinds of complicated patterns? But, and this is key, we need it to do that without just memorizing every single data point, noise and all. We clearly need a totally different way of thinking. So that's what we're doing today. We're going to build a decision tree regressor right from scratch. We'll start with the big idea, then we'll get into the real engine of the thing, how it finds the perfect place to split the data. After that, we'll watch the tree grow, see how it actually makes predictions, and then wrap it all up with a good old-fashioned pros and cons list. So instead of trying to find one single master equation to fit all the data at once, the decision tree uses a classic divide and conquer strategy. Seriously, just think of it like a flowchart or maybe a game of 20 questions that it's playing with your data. And here's the more formal take. It's a model that learns a series of really simple, intuitive if-then-else questions to predict a number. It's what we call a white box model. And that's awesome because unlike some super complex black box algorithms, we can literally open it up and see exactly why it's making the decisions it's making. At its heart, the strategy is so simple it's brilliant. We just want to chop up our data into smaller and smaller buckets. And the goal for each bucket is to have the outcomes, like house prices, be as similar to each other as possible. In other words, we want to reduce the chaos, the mixed-upness, the variance within every little group we create. Okay, so this is the absolute crucial part. How does the tree figure out where to make that split? This isn't random. It is a very clever, calculated process to find the most powerful questions it can possibly ask of the data. This is the magic of the algorithm. Let's use a really simple data set here to build our intuition. Imagine we're real estate gurus trying to predict house prices. We've got 3 features to work with: the size, the number of rooms, and the age of the house. Our mission is to create a set of rules to predict that final price. So at the very beginning, all of our houses are just thrown into one big pile. We call this the root node. And inside this pile, the prices are all over the place, right? 150K, 400K, 250K. It's a mess. This group is not homogeneous at all, which means its variance is super high. Our first job is to find the single best question that can split this one messy group into 2 cleaner groups. Now, to measure how clean or pure a group is, we use a metric called mean squared error, or MSE. It sounds fancy, but it's not. For any group of houses, you just calculate the average price. Then you see how far off each individual house is from that average. A high MSE tells you the prices are scattered all over. A low MSE tells you they're all clustered neatly together. The algorithm's entire goal is to make splits that create new groups with the lowest possible combined MSE. So how does it actually test a split? Let's say the question, is the size less than 1,300 square feet? It's a simple 4-step dance. 1, it already knows the MSE of the group before the split. 2, it splits the data into a yes pile and a no pile. 3, it calculates the MSE for the yes group and the MSE for the no group. And 4, this is important, it calculates a weighted average of those 2 new MSEs. Why weighted? Because a split that makes a tiny pure group and a huge messy group isn't as good as a split that creates 2 decent-sized, pretty pure groups. The algorithm will always pick the split that causes the biggest drop in MSE. And this shows the goal perfectly. You start with one big, messy group with high MSE. A good split gives you 2 new groups that, when you look at their combined weighted MSE, is much, much lower. We've literally created more order from chaos just by asking one smart question. The method the algorithm uses is called a greedy exhaustive search. Sounds complicated, but it's not. Exhaustive just means it's incredibly thorough. For every single feature, it checks every possible split point. Size less than 900, size less than 1,100, rooms less than 3, age less than 7. It tries them all. Then the greedy part comes in.
It calculates the MSC reduction for every single one of those options and greedily picks the absolute best one for that single step without worrying about what might happen later.
So we found our first best split. Awesome. But we don't stop there. This is just the root of our tree. Now we have to apply this exact same logic again and again to grow all the branches. The algorithm just keeps going. It takes that yes group from our first split and asks, okay, what's the best way to split this smaller group? And then it does the exact same thing for the no group. This process repeats level after level, recursively building out that entire flowchart of decisions until we have a full tree. Of course, this can't go on forever, or you'd have a leaf for every data point. The tree needs to know when to stop growing. There are a few common rules for this, like hitting a maximum depth you set beforehand, or when a group just gets too small to split meaningfully, or, and this is a good one, when making another split just doesn't really reduce the MSE by any significant amount. Okay, so the tree is fully grown. We're almost there. We have two final jobs. Figure out how to actually use this thing for predictions, and just as critical, make sure we haven't let it grow too perfectly. Making a prediction is actually the easiest part. You take a new house, let's say it's 1,100 square feet with 2 rooms, and you just drop it in at the top of the tree. Is size less than 1,300? Yep. Are rooms less than 3? Yep. And boom, you've landed in a final leaf node. Your prediction is simply the average price of all the original houses that ended up in that very same spot. But here we find the single biggest danger of decision trees, overfitting. If you let the tree grow until every single leaf is perfectly pure, it has essentially just memorized your training data. It's learned not just the real patterns, but all the random noise too. And this creates a model that looks like an A+ student on the data it trained on, but completely bombs the test on any new data it's never seen. The solution to this is a technique called pruning. And it is exactly what it sounds like. After you grow this big, potentially overgrown tree, you go back and strategically snip off branches that don't really add much predictive power. It makes the model simpler, more robust, and way better at generalizing to what it'll see in the real world. So there we have it. We've built the tree from the root all the way to the leaves and even pruned it. Let's take a step back and look at the final report card for the Decision Tree Regressor. So what's the bottom line? Well, on the plus side, its biggest win is how easy it is to understand. You can literally show those if-then rules to anyone. It also handles those messy nonlinear patterns we started with, and you don't have to do a lot of data prep. But on the downside, its greatest weakness is that greedy process. It's so focused on the best split now that it can easily overfit. This also makes it a bit unstable. Sometimes just a few changes in your data can cause the whole tree structure to change completely. And that leaves us with a really deep question that's at the heart of so much of machine learning today. In a world with these giant neural networks and super powerful black box models, when is it better to pick a model that might be a tiny bit less accurate, but is completely transparent and understandable? It's that constant trade-off between raw predictive power and genuine human insight.